They discovered the Higgs boson. Okay, so now what happened?
So here's the deal. Here's why I bring this up, because it's what is known as a scalar field. So when you think about the fields that you know of, right? They're like, oh, the electric field, I have a charge, it has an electric field. Magnetic field, I have a charge that's moving, it generates a magnetic field. Gravitational field, oh, there's this matter. So every field you know of, there's some source in matter. But then here come the particle physics. They're like, oh yeah, you know why every electron is identical? Because they don't say it this way, this is mine. You know why every electron is identical? Same reason every C note, musical note, is identical, because they're not the real thing. The real thing is the string or the air that's vibrating, right? So they invoke this idea of quantum fields. So the quantum field just permeates all of space-time and is just there.
But nothing is real in that quantum field.
Excitations of the field are our particles, right? So they're the permanent ones and they're the virtual ones, right?
So we measure the excitations as particles.
As particles, right. Now here's what happens though. They say, oh, there's this thing called the Higgs field. It's just there. It's just everywhere in space at all times. It's just there, right? Scalar field, no source. And I'm like, in my mind, as a young scientist, I'm like, is that real?
I've always been bothered by physicists' preoccupation with conservation of information, especially in regard to particles falling into a black hole. Firstly, it sounds more like a philosophical position than one derived through mathematics or scientific method. Correct me. Secondly, Mr. Heisenberg taught us that one can never know all information about a particle. Thus, can't we consider that information to never have existed in the first place and thus can't be destroyed? I have one thing for Alan. Alan, if you're going to ask a question on acid, you got to send the tablets to us too, so we can be on the same wavelength and answer the question.
Tablets?
Go.
You mean tabs?
There you go. There we go. There we go. There we go. Alan Geis, go ahead. Answer that question.
He actually remembers the 60s.
Yeah, exactly.
If you lived in the 60s, you shouldn't remember.
There you go.
All right.
Yeah.
So I like that. So
I say here. I say here.
Catch us up on the information.
This is a cultural phenomenon. Nerds ain't cool, and so they try to make something cool that ain't cool. All right, so this whole thing about do black holes have hair?
He's from Denmark. I read recently that the universe is expanding too fast for our theories and models to fit, increasing the Hubble tension. Do you think the problem is with our models, or is there some physics we just haven't discovered to explain this? I.e., is the rate not constant due to some undiscovered property of space-time?
Or is there something wrong with the data? So are models off? Do we trust the data, or do we need new physics? So now tell me about the latest NASA acronym.
Yes,
Interstellar Mapping
and Acceleration
Probe.
But you can't have a thing that says IMAP and then the word mapping is in the middle of it.
Yeah, that's bad.
It's not working. We're going to have to redo this.
The word in the acronym can't be in one of the words of the acronym. If you were to fly on a 747 from the United States to Europe, and every time you did that, they took the plane and shoved it off a cliff and rolled out a brand new one, your cost of flying to Europe would be thousands of times higher every time you did it, possibly even more. You'd be paying millions of dollars to fly to Europe every time. But we reuse the airplane. Yeah, in between, the engineers check it out, they kick the tire, they make sure everything's working. You have a diagnostic list to make sure that everything checks out, you put it back in motion. So not only do you want to reuse the parts, you want to fly them as often as you possibly can. Because as is true with most businesses, there's the cost of the mission itself, but then there's the cost of the marching army.
Want that gig?
No, I don't want you to have the gig.
We might have to fight about it now.
No, you'll lose.
Okay, you ready? Let's try it.
Here we go.
Ready?
Okay.
Let's audition. This is our audition for CNN. Ready?
Replacing James Hill. Should Marmy go first?
Yeah,
oh, great.
Absolutely.
This is CNN.
That's not bad. It's actually pretty good.
Oh.
This is CNN.
Ooh, that sounded a little more authoritative. Let me try again.
All right, go ahead.
Because you hit the syllable sharp there.
This is my wheelhouse, bro. You know what I mean?
Okay. Okay. All right.
Come on.
This is CNN.
Nice.
The estimate for the chances of it hitting us are down at this moment, between 1% and 2% at the time of this recording. Now, what does that mean? I'll tell you. It means that the orbital trajectory we have for it, when projected forward in time, has an uncertainty cone where the asteroid could end up anywhere in that cone, but more likely in the center of the cone. If it stayed in the center, you can ask, how close to Earth would it come? About the distance from Earth to the moon. Now, let me remind you how far that is. You may remember NASA had a mission to an asteroid to try to deflect its orbit, sort of as a test case in case something might be headed our way. Now that it has done that, knows how to do it, learned that it was successful, it gives us a little more confidence going forward for any subsequent asteroid that's discovered that might actually be headed our way. By the way, any country that has a planetary defense office is perking up right now because of these risks that we now know and can track. In fact, China, just as an example, didn't have a planetary defense office until this asteroid's risk was calculated. We can only be safer in this world if everyone thinks about this problem in a coordinated way. Together. Oh, I got another one for you.
That's so great.
Ooh.
Go ahead.
Ooh.
Go ahead.
A pendulum is harmonic motion.
That's harmonic motion.
You want to describe a pendulum? And where's the pendulum moving the slowest?
At the very
top. At the edges.
Either end. Either end. Yeah.
And gravity is the force, the restorative force in each direction. And that's going to have a sine curve in it. In the solution to that equation, a pendulum takes the same amount of time to complete a swing, no matter how wide you swing it.
I recently watched Side Channel with Akeem. It was about gravitational waves. Just wondering, can they also alter time? If a huge collision occurred near our solar system, how would we feel them? Would we be alive to physically notice?
So will it do damage, first of all?
Yeah.
And we know it's a disturbance in the gravitational field, and everybody knows after the movie Interstellar that if you're in a different gravitational field, you're going to age differently.
Yeah.
So what kind of consequences?
That's a good question. Like the perturbations of time travel. This is a good time to bring up the Andromeda paradox.
Okay, that's what I was thinking the same thing.
The Andromeda paradox is the fact that if you and I are looking at Andromeda,
the galaxy.
The galaxy.
Not the stars that make the constellation.
Right. Yeah, not the constellation.
And not the strain that killed millions of people.
Not the Andromeda strain, right? 2.5 million light years away. Then what happens is, suppose you're sitting in your chair and I'm running by. And at the second I run by you, we both look up at Andromeda. Because I'm moving and you're stationary, we're going to see events that are days apart, even though we're in the same location looking at the same time.
How can that be?
You think that relativity, and you think that the light
say relativity and keep talking.
How far? Wait, in this scenario, how far away from me are you when you're running by?
You're in the same place.
We're in the same place essentially.
So you're like literally running.
I've never heard of this paradox.
And you look up.
It's a little known paradox.
And the thing that you see and I see are days apart.
Days apart
because of our physical perspective.
Here's what you would think. You would think the light is arriving right now. We should all be receiving this light, but that's not how it works. Motion changes the perception of time. And so we know about that in terms of the local universe. We call it relativity of simultaneity, right? You're moving, I'm not. You see events as simultaneous.
We say the particle can also be a wave.
You know, that's a very interesting point. I want to compare notes with you about how you learned wave-particle duality. Because I went through the educational system a few years after you did. And it might have been a transition.
You think something magic happened between those two times?
In the pedagogy, not in the physics.
Okay.
In other words, when I was brought in through the system, the first thing I was told was that waves and particles, everything is a wave and a particle.
That was not the first thing that I was taught.
That is really true. Yeah,
that's later in the book.
In high school physics, straight up ordinary high school physics, I was taught the de Broglie relation. It relates the momentum of a particle to its wavelength. And the relationship is mediated, shall we say, by Planck's constant.
Wait a minute, I pronounce it de Broglie.
Is it possible that dark matter is something that could travel faster than light? What is your theory on that?
Yeah, well, we have those tachyons. Is it tachyons? Is that what it is?
If dark matter is some kind of matter. We're calling it matter, but we don't know what it is.
No, here's the thing why we know it's not that. Because there are these two models. It's not moving faster than light. Because the two models that were competing were, is it hot dark matter or is it cold dark matter? So particles moving very fast would be hot dark matter. And we know that the best model is lambda CDM, cold dark matter.
Dark matter just feels, every time I read about it, it just feels like, I don't know, like a guy shows up at a party or something and it's there, but it's a weird vibe. It makes
the only thing
it's the person that makes
axions, and I don't find that to be well.
People making up particles that'll do this.
Yeah. Well, they made up a particle to cancel out the electric dipole moment of the proton, which should exist, right? If the quarks have electric charges and there's separation between the minus and the negative, there should be some what's called separation between them, which we call a dipole moment. But one is not measured. So Helen Quinn et al., they came up with this idea, maybe there's this other field that cancels it, because essentially what happens is the sun accelerates particles, right? It creates this bubble. And the example—
That's the solar wind.
The solar wind,
Yeah.
right?
So the heliosphere,
but it's moving
right?
fast. It is supersonic,
Right.
The heliosphere.
Yeah.
But when it hits
Wait. What do you mean supersonic if it's moving through the vacuum of space?
space, is it exactly a vacuum?
Oh, it's approximately a vacuum.
It's approximately a vacuum. Yes,
Okay.
it is. Yes, it is.
Okay,
yes.
so cool. So it's moving
Yeah.
faster than the speed of sound would be in that very reduced vacuum.
Exactly.
But
Yes.
I find intuitive.
Yes.
All right. So one of them relates to the Heisenberg uncertainty principle.
Yes.
So the way it gets misconstrued, of course, is people say there's the observer effect, and is your consciousness affecting the experiment? Oh my gosh! Let's hand it over to the New Age folks and let them solve it. And this is a complete misunderstanding of quantum physics. And so when you explain it and you say, well, we are big macroscopic objects. If you're going to take a picture of us, turn on the lights and we take a picture. But the smaller you are, no longer are you so immune to the consequences of being illuminated by photons.
That's right.
Right? And so if I'm a particle and I say, I wonder what the particle's doing. Let me take a picture. And then you turn on the light